Hi, my name is Jeff Washburn, and I'm a Vice President at DeepIQ. During this session, we will explore how you can develop cutting-edge AI workflows on both streaming and batch data that combine time series data like Pi, SCADA systems like Ignition. We will examine how you can ingest IT sources like SAP and Oracle within minutes. We will take this ingested and prepared data and use it to power your digital transformation. I will be using DeepIQ's Data Studio toolset, which highly automates self-service analytics for the industrial world. First, a little bit about DeepIQ. DeepIQ is a Houston-based company with offices in Calgary, Canada, and Hyderabad, India. We were formed with the concept that 80% of effort in an industrial data analytics project is non-value add. Data Studio was developed to highly automate these tasks to reduce the time to market and to eliminate the technical friction in analytic programs. Data Studio can enable your data scientists, subject matter experts, like process engineers and geoscientists, and data engineers to quickly mine geospatial and operational data, and build, analyze, and deploy an enterprise solution that will run on any cloud platform. You were looking at the user interface of Data Studio. We have created over 175 click and drag components. Each component represents a time-consuming and tedious task common for data analytics workflows. Let's take an example. We drag an OSI Pi component onto the canvas. This component contains all the code that will connect to your Pi server. In the properties, you configure the location and security along with what tags are needed for your workflow. Similarly, you can connect to your SAP and retrieve the business data by configuring a simple component. That is all that is needed. When you are finished with your workflow, Data Studio will generate the needed Spark code that can run natively on your Databricks environment. Data Studio is designed to work with the Databricks execution environment. Together, your workflow is distributed to take full advantage of your cluster to get up to 50x greater performance. We are leveraging the native capabilities of Databricks to achieve this scalability. All the workflows you build work in a distributed and parallel manner and scale to hundreds of nodes if required. But DeepIQ is a simple containerized app that uses cloud to auto-scale based on compute requirements. On the left are the building blocks of Data Studio. Since we are limited on time, let me say that we have components for the relational, time series, and geospatial data. I'll be showing you some of that. We have comprehensive components for structured and unstructured machine learning, along with time series analysis. On the time series analytics, you might want to remove the outliers. We have components for ETL, including change data capture. Our structured learning on geospatial data is beyond leading edge, but that's another webinar. Databricks is a unified data and analytics platform that provides data science workspaces, reliable data lakes and data pipelines, and enterprise cloud services for its client. The Databricks runtime is built on top of Apache Spark, and thus completely abstracts out the infrastructure complexity and the need for specialized expertise to set up and configure your data infrastructure. Databricks provides a Spark engine that is faster and performant through various optimizations at the I/O layer and processing layer, or the Databricks I/O. Delta Lake is an open source storage layer that brings reliability to data lakes. Delta Lake provides ACID, transactions, scalable metadata handling, and unified streaming and batch data processing. The architecture illustrates how DeepIQ's Data Studio integrates perfectly with the Databricks platform and Delta Lake. So the scenario we're going to use in this webinar is Acme Operating Company. This company has thousands of wells. These wells have different artificial lift types from gas lift, electrical submersible pumps or ESP, and progressing cavity pump or PCP. Due to the downturn in the oil and gas industry, the company is now exploring all the ways of reducing their operating expenditure. Recently, there has been significant increase in the production cost of their ESP wells. Acme would like to use their data to develop a machine learning model to predict the issues in operating these wells. Let's look at how we can solve this problem. Acme uses OSI Pi as their data historian for their gas lift wells. ESP wells are in a different field which they acquired recently. That field uses Ignition SCADA software from Inductive Automation. By the way, we are OSI Soft and Inductive Automation partners. Not only do we support OSI Pi, we have also developed components that connect to the leading SCADA data providers, such as GE Prophecy, IP21, as well as industrial standards like WITS-ML and OPC UA. SAP is their system of record for all maintenance-related information. To build the machine learning model for ESP operations, your data scientist and SME will need data from 3 different sources: operational data from Ingestion and maintenance record from SAP. Before we jump onto a machine learning model, let me share a few thoughts on OSI Pi software. As you know, they are the market leaders in data historian world. There are different ways that you can connect to Pi. The first is to use the JDBC driver. This gives basic access to the data. The second is to use the Pi Asset Framework Software Development Kit, or ASFDK. This is a far more comprehensive connection that gives access to all components, including historian and tag relations. If the Pi server is in a remote area or has connectivity issues, DeepIQ has an edge component that provides store and forward capabilities, along with a compression algorithm that dramatically lowers the transmission footprint. Once the OSI component is configured in Data Studio, the Data Studio execution environment on Databricks is used to retrieve the streaming or historical data. Typically, there are numerous issues with time series data. Often the data is out of range, or there can be timestamp issues such as clocks that are not synchronized. There can be delayed signals and divergence. Often the sampling is inconsistent, or the sensor acquiring the measurement is over-precise. There can be missing data or missing metadata, which is needed for the analysis of the data. There can be missing foreign keys or provenance. There can be latency mismatch to the actual time during which the process or event occurs. The solution to these issues is to use the time series analytics components in Data Studio. We have built dedicated functions for time series data that automates data cleansing, smoothing, outlier handling, data imputation, and other time series analytics. Most advanced components available. Let's go have a look in the first demo, and I can show you some of these components. So let's have a look at our first demo. You're looking at Data Studio, and this is the workflow that we've created for our particular demo. Let's have just kind of a quick look at it at a high level, and then we'll jump into the different areas. The first thing we're doing is we are ingesting data from our gas lift data from OSI Pi. Next, we're going to have ESP data, which is coming from Ingestion. We're now going to have our maintenance data, which is coming from SAP. We're going to merge those 3 data sources, and then we're going to do some machine learning over here. In this first demo, we're going to take a look at just how the OSI Pi area works here. And let's zoom in a little bit on this side. So the first thing we have is our gas lift data coming from OSI Pi, and I can look at that data and kind of see that this is the operator, the asset, the property, equipment group. All of this data is coming in. Next, we can extract just the wells that we're interested in. The window group. The goal of window group is to support this MAD outlier removal component. The window group uses neighboring data values to average out the new points. We then have put the window group back together, and then we have the ability to fill in any missing data that is not there using a rolling impute method. Let's look at some visualizations. Here, I'm going to put the date on my x-axis, and I'm going to put my THP on my y-axis, and I'm going to create a plot. Let's expand this up. And what we're looking at here, this is the data that is coming out, the raw data that is coming out of our OSI Pi environment. There's a couple of things that are pretty obvious. First, you can see we have some outliers here. This is data that is outside of the normal, and we need to remove that for our model to work properly. Secondly, you can see there's a period of data here, period of date here, where there is no data at all. Okay, so let's go ahead and look at in the workflow what is the result of this. So now that we've gone ahead and run this remove outlier, let's have a look at the visualizations for that. Same thing, I'm going to put the data in the x-axis and the THP on the y-axis and create the plot. And what you'll notice here in this particular case, all of our data is now flat. Those outliers have been removed. And then finally, let's look at the results after we have done the filling of the missing data, or the data imputing. Same thing, I'll put my date on the x-axis, my THP on the y-axis, and create that plot. And we can see now that using the neighboring numbers that we talked about earlier, all of the data has now been filled in. So our data has now been prepped and ready to go for modeling. There's one more component I want to have a look at, and that is this reading ESP data from Ignition. When I hit the little drop from here under the summary, we can see that here's the resulting of this ESP data that's coming from our Ignition environment. Okay, let's go back to the slides. Now let me show you various relational data connectors available in Data Studio. We have SQL Server, Oracle, MySQL, and others. This is typically where the maintenance, failure, and ERP data is located, which we use in this scenario. SAP is commonly used in industry for ERP data. There are two different ways you can connect to SAP. The first is through the JDBC driver. This gives you access to all of the tables and views in SAP. However, the data model in SAP is very comprehensive and deliberately obfuscated. Data Studio provides a connector using the Business Application Programming Interface, or BAPI, in SQL. This interface enables the user to select the business object they are needing for the model, such as production values or work orders. As a side note, Data Studio also supports the ingestion of geospatial and unstructured data. We support formats such as GeoTIFF, GeoJSON, and shapefiles. This enables your modeling to have a geospatial flavor, such as where a pattern exists. Often the relational data has to be prepared before use in a model. This can be trivial items such as removing duplicates or dropping columns, or it can be complex items such as change data capture to allow for modeling data over time. We have a robust SQL query editor which I will show you to refine your data to the needed point. Now let's have a look at how Data Studio handles relational data, including our SQL query component. So in this demo, we're going to extract the maintenance data out of SAP. So I'm going to use this data transformation component. We can see that the data that's coming in is a list of all of the maintenance items that are for these particular ESP pumps. You can see when a ticket was created, job started, well restarted, etc. Next, we only care about the pump maintenance data. So we're going to filter out that data so that only the data that we care about is there. Finally, we're now going to merge together the maintenance data, the ESP data, and the gas lift data in this join component. This join component is based on SQL-like querying. So when I come in and look at the data for this, you can see it's got a simple query that go from my different inputs and on the join. Now Data Studio's got a great tool called Query Builder that enable our users to build queries on the fly. You can see here I've got input. It auto reads the values that are coming out of the component below, so the fill missing data, for example. I can add in additional data sources. Perhaps I want the ESP data, what type of join I want to happen on this, and then what columns we join together. We can then choose what particular row we want, if we wish to count, min, etc. We can do custom where clauses, custom group by clauses, and it will build the SQL query along here. All right, let's go back to the slides. As mentioned before, the goal of ACME is to reduce OPEX by identifying potential issues in their ESP wells. DeepIQ believes in one fact: empowering data scientists and SMEs to leverage domain knowledge and physics to build model quality. As you saw before, Data Studio's various features help our users extract good historical data by using smart data filters swiftly. Once the fully validated machine learning models are ready, you can use them in your real-time environment to predict anomalies in the operations as soon as they happen. For example, back pressure in a flow line, which could lead to an ESP failure. This helps prevent potential equipment failure, or at least predict them a few days in advance to minimize the maintenance costs and downtime. After combining cleansed data from Pi, Ignition, and SAP, now we have a workflow to focus on one ESP well which has multiple issues in the past few months. Hence, I am first extracting data of that well and then removing all data associated with the failure for model building purposes. Here in our workflow, you can see that this is a combination of all of the data from Pi, Ignition, and SAP. We're only interested in the ESP1 data, so we're going to just filter it out so we just have our ESP data here. Next, we're going to ensure that the timestamps are common and work across the different systems. Next, we have a custom component that allows us to split ESP data into each period that a pump was operated. These are called cycles. Now, to ensure a better model prediction, we're going to remove the failure data. Next step is to split the data into two buckets, one for training and a second one for blind testing. Okay. In this example, we are using a random forest model to predict the gas production volume as a function of various operating variables, including ESP current and flow line pressure. I would like to stress one point that SMEs play a pivotal role in the variable selection process as the physics of the process needs to be captured correctly. Let's look at the properties of the random forest training. Here, I can specify, for example, the features that are of interest for this particular model. For example, casing pressure, downhole pressure, etc. Every time that you build a model, there are parameters that need to be selected by your data scientists. The data scientist will tune the model to get the best results. Data Studio allows for this. However, if you would like a Data Studio to generate the best performing parameters, we can do a grid search and effectively try hundreds of combinations to come up with the best parameters for that model. Here you can see I have my grid search set to true, and down below I can specify the hyperparameters that are needed. So next, let's have a look at the results of this trained model. I'm going to go into the summary and then select this. You can see, let me scroll down a little bit. These are the results of the feature importance that were suggested by our model: water temperature, casing, downhole pressure, and current. As well, we can see the results of the trained model. Here we have 0.972% or 97.2% accuracy, which makes this a very good model. Further down, we can see the train metrics and the train hyperparameters. Now that we have a trained model, we use that model to generate results against both the training and the testing data. We do a little formatting, and then the compute percent deviation will compute the difference between the predictions and the actual data. Now let's have a look at some visualizations. So the model we generated is predicting production based on the inputs that were supplied to the model. What we're seeing here is a percentage difference between the actual versus the predicted values. For example, in cycle 3, there is a value of 0.226, which indicates that our predicted value is within 0.2% of the actual value. Here are two plots in which a subject matter expert and data scientist would typically review. The first one shows how good the training was, and the second one is the result of the blind testing. As you can see that during blind testing, the application smartly identified the flow line back pressure issue, indicating that with streaming data and the machine learning model would predict such an issue well in advance to take appropriate action to eliminate the ESP failure or to plan maintenance activities proactively to keep the downtime to a minimum. I hope you have found this webinar interesting. My name is Jeff Washburn, and I would love to continue this as a conversation. Please reach out to me at wjeff@deepiq.com.